Does adding wings to a motorbike make it more aerodynamic? And if so, how? That is what we're looking at today. For a normal motorbike, the front fairing is wingless, and that is nice for aesthetics and even functionality to some extent. But for high-performance bikes, this misses a potential opportunity to make the motorbike produce much more downforce. A few weeks ago, we did a podcast about those vanes at the bottom of the motorbike, and they were incredibly good at redirecting the flow and increasing downforce. As a result, through the corners, the rider could travel faster, hence go around the circuit much quicker. But these aero devices were low down, leaving much real estate higher up untouched. What if we put wings there? So to find out if putting wings on the front fairing helps a motorbike's aerodynamics, we're looking at this paper here today called Numerical Study of Motorbike Aerodynamic Wing Kit. It is open access, so you can find the link below. And just a heads up, there are some really cool findings here, along with some very cool CFD. So you might be looking at this paper and seeing that this watermark called Original Unedited Manuscript over it. Well, this paper has been published and is available on the journal's website, and it's just a few days old in this format. Fortunately, the figures are still clear, so we can see them unedited. So let's dive in to see what the wings did and how they performed during the tests. Now, these aerodynamic wing kits, which are known as AWKs for short, have been around since 2006 or so, at least in competitive motorbike racing. So Ducati sported it back then, and then it wasn't until about 2020 that a motorbike with an AWK won. Since then, AWKs have become all the rage, and because each team is competing against each other, the exact results of each team's AWKs and AWK in general performances are a little secretive, so we're not really sure exactly how they affect the motorbikes. And because they're airfoils, you can change so much about them. There's the chord, the camber, angle attack, where the maximum thickness and camber occur, and trailing edge thickness, just to name a few parameters that you can change. There are even more than that though. So if you were to select an AWK without much knowledge about its performance, and then it performed well, then chances are that in general AWKs would be good, because that's just luck of the draw really. But the question that needs to be asked is, why would you want an AWK on a motorbike? Does it hold more potential than other devices? Well, yes it does, and that is due to the nature of the motorbike, and motorbike racing in general. So power is supplied to the rear wheel of a motorbike, which makes the motorbike want to wheelie when you accelerate, because that's where you put the power through. So producing downforce at the front of the motorbike will help counteract that. And it's not just a matter of producing downforce anywhere over the motorbike, but where you produce it as well. So to that end, AWKs are prime devices to produce the desired downforce at the right locations. Now, like all airfoils, you need to consider the performance you need as well before you even do anything. So if you were to just run airfoils too high in an effort to maximize downforce, so you put it at a very high angle attack, you run the risk of triggering stall and losing much of that downforce you would originally produce. On the other hand, if you were to run them at too low angle attack, then you won't be producing as much downforce as what you could be getting, and you'll need to make the entire wing bigger. And there are rules governing how big they can be to begin with. So for example, the entire bike can only have a maximum width of 600 millimeters, so 2 feet wide, as shown in figure 1b if I scroll down to here. So just here, 600 mil wide just there. At very best, that means that the wings can only have a width of 300 millimeters, but in reality more like 150 millimeters or so, given that you have actual motorbike as well to take up some of that width. So we come across the age-old question and problem aerodynamicists have encountered, which is designing the best airfoil for the given application. So that also feeds into another problem for motorbikes, which is the front fairing is one of 3 main aerodynamic contributors to the drag of the entire motorbike. The other 2 main contributors are the front wheel and the front suspension. So these 3 components produce the majority of the motorbike's drag. So tacking on airfoils onto the front of the fairing might make an already problematic area even more problematic. With all that in mind, these researchers decided to stick an AWK on a motorbike with a human figure on the motorbike as a dummy variable, and the airfoil profiles they selected were NACA 4412s. So if you don't know, NACA 4412 airfoils are one of the most common airfoils found in aerodynamics and is the basis for many airplane wings. And when you look at research, there's a good chance you're going to find a 4412 in the paper that you're looking at. The other common ones are NACA 0012s and NACA 0020s, but 4412s are very common. So this 4412 has a maximum camber of 4% of the wing's chord, And this maximum camber is located at 40% downstream from the leading edge, so about halfway almost. It also has a maximum thickness of 12%, which occurs 30% downstream from the leading edge as well. So the maximum thickness occurs just upstream of the maximum camber. And this NACA 4412 has a maximum lift coefficient of about 1.6 and a minimum drag coefficient of about 0.08. The maximum lift to drag ratio, which is a measure of the airfoil's efficiency, is about 130, which is really good. Most airfoils struggle to break about 100, so 130 is really nice. But just because this airfoil is good for aviation doesn't mean it's good for motorbikes, as we'll see later on. Maybe it is, maybe it isn't. While the airfoil profiles they used were fixed, they did test a number of different configurations though. So they obviously tested the motorbike without airfoils, that's the baseline case, just to see what's happening. Then they looked at just one wing on each side and how it performed by rotating it from 0 to minus 51 degrees, So minus 51 degrees is huge. Past about 20 degrees, the airfoil in clean flow starts to act less like an airfoil and more like a blunt paddle. But interestingly, in proximity to the bike, the maximum lift to drag ratio of the airfoils they found occurred at minus 37 degrees. So that means that the motorbike is changing the flow around the airfoils enough to push the best angle of attack to 37 degrees. That's insane. So using this information, they then tested a few more setups. The next one was called Case 3, where they wanted to see how having two wings on each side, while not necessarily parallel to each other, affected the motorbike. So the upper wing was installed at minus 37 degrees, and they found earlier that's because it worked best. But then the lower airfoil could rotate about from 0 to minus 61 degrees as well. Then for the next configuration, Case 4, as shown in figure 1b here, this one here, they had two wings on each side of the fairing, but they decided to fix them parallel to each other, so they could move, but they could only move together. And finally, they used the information from cases 1 to 4 to make Case 5. Now, up until now, cases 1 to 4, or I guess case 2 to 4, didn't really abide by FIM regulations, which are the International Motorbike Regulations. So Case 5 was made to make these wings compliant, because at the moment, cases 2 to 4 present a safety hazard having just these wings coming out. So this meant that the wings in Case 5 must be rounded at the tips and make a closed shape at the front, around the side, around the wingtips. So the leading edges must meet, as we see, and shown in figure 1D. These reasons are for their safety requirements. So I guess if a rider comes off, they're not going to hit this thing and hurt themselves too badly, hopefully. Even still having wings there, that's quite a lot. But anyway, to investigate all these cases, the researchers used CFD, and there were some pretty impressive aspects of the CFD setup. So let's get into it. So the CAD geometries were put into a domain as shown in figure 2, which is very large actually, by the way. That's good. They tested these geometries at 3 different velocities to simulate different racing speeds. They were from 20 meters per second, so 72 kilometers per hour, up to 100 meters per second, which is 360 kilometers per hour. So imagine trying to hang on to a motorbike at this speed. You have to really punch down, otherwise you're going to blow off. So, as I've covered in one of our Aero fundamental videos, number 48, which is called When is Air Compressible? So the general rule of thumb for pretty much ever really has been that when the flow is above Mach 0.3, the flow can be treated as compressible, and below it, it can be treated as incompressible. The assumption is that below that value, Mach 0.3, the changes in density aren't really great enough for us to consider the compressibility effects. Well, this rule kind of came about maybe about 80 years ago, so maybe even more, and that was definitely true back then. But in modern times, with the accuracy of the instruments that we have today, that rule of thumb doesn't really hold much. I mean, in that video that I mentioned, I go through the math showing that at a Mach number of 0.3, the error in the air density is around 5%. So that's really big. So personally, I don't think that you can treat air as incompressible up to Mach 0.3. I think more around 0.1 is more accurate. In this study, the researchers still went for the incompressible solvent in open foam for their 100 meter per second flow, which is around Mach 0.3. And I think they should have really gone for a compressible solvent instead. So probably pimple foam or piezo foam or something. Rope pimple or something like that instead of the pimple and simple foams. If you don't know what I'm talking about, don't worry. On that note, if you want to learn how to do open foam, check out the links below. Anyway, Now, one good thing is that they treated the walls of the simulation as slip, which is crucial when doing an automotive simulation. That results in no boundary layer forming and hitting the motorbike and hence replicating more real-life conditions. Because when you're on the road, there's actually no boundary layer forming unless there's a wind coming on and creating a boundary layer that way. But if you're just going along the road and there's no wind, you're traveling through the air, doesn't actually create a boundary layer on the road in front of you. So that's good that they've done a slip condition here. So one really impressive thing is they first did URAS simulations, which they used for cases 1 to 4. But for case 5, they then used the URAS results as the initial conditions for the LES simulation. So they ran case 5 as LES. Now, running LES on an entire motorbike is pretty impressive. The question is, how many cells did they need, and is it feasible? So in table 1, we see the results. So I'm a little surprised actually, because from 14.9 million cells onwards, the drag and lift coefficient, so these two values here, were very similar. And even when you have a mesh with over 10 times the number of cells, so 163 million cells, the lift and drag coefficients are still pretty much bang on. So that shows that for this motorbike, at a velocity of 100 meters per second, at least when they're treating it as incompressible, you only really need a mesh of around 15 million cells to run a grid convergence LES simulation. Sorry, grid converged LES simulation. You don't need any more than that to overcome any errors based on the grid. So I'm quite surprised because I have used that many cells on just an airfoil before. So to get the lift and drag coefficients of the entire motorbike with 4 airfoils, it's quite impressive to me. So a few more details about their setup. So their URAN's turbulence model was KME SST, which I'm happy to see. It's great that this turbulence model is gaining more and more traction, it seems, every day, and replacing the more outdated and less accurate ones like the Capsule family, for example. For their setup, they used the Smagolinsky SGS model and resolved about over 80% of the estimated kinetic energy. That's pretty good. The Courant number, which tells us effectively how many cells a piece of air will travel through in one time step, was less than 1 for all cells. So that corresponded to a time step of 10 microseconds, which I am a little surprised considering their finer details on this bike that I would have thought would have needed smaller cells to resolve, but maybe there was enough. And their Y plus value was below 1 for the entire motorbike, which is good. So up until now, I would say that they have a near perfect CFD setup. They've done everything right, from the turbulence model, the Courant number, to the Y plus values, to LES turbulent kinetic energy resolutions, to a good grid independent study, and which shows convergence. It's really good stuff here. One final note is that for cases 1 to 4, where they only used URANs, they only went with a 2.2 million cell mesh. And it is difficult to tell if that is enough when it comes to really the only weakness of the CFD, and that is that they don't have any validation data. So we can't really tell exactly if this number of cells was good enough, and also, generally speaking, if the CFD was accurate, because there's no validation data. That's literally just one major weakness. Everything else seems really good with the CFD setup. So it's kind of like they've fallen over the finish line. They literally only have validation of the airfoils on part of the front fairing with Java foil, which is an okay software to begin with, but is no substitute for experiments or other validated CFD, or even for a motorbike fairing. For airfoils and airfoils at pre-sliding to attack, Java foil is really good, but that is not what we are really dealing with here. We have other things as well. So I'm a little disappointed here because they have everything going right for their CFD up until now, and they have a really good chance of having a very trustworthy CFD setup. But then, like many other CFD setups, I don't think we can trust their lift and drag coefficient data that much. The flow vis data is good. I think that's fine. But the force data, I think we need to take with a grain of salt because there's no validation data backing it up. So overall, because the rest of the CFD was really good, I think we can give this around maybe a 7 out of 10. So let's move on to the results, because the researchers did something that I think is really cool. So a lot of research regarding motorbikes often omit the rider. This research doesn't, and in fact, they also looked at the effect of the rider on the forces. In figure 5, they have the lift to drag ratio, and the drag coefficient of the motorbike with just one wing, so case 2, with and without the rider. So the rider, without the rider on the left and with the rider on the right. And the single wing on each side was tilted from 0 degrees to minus 51 degrees, which I've said minus 51 is huge for almost any wing. The only wing that can really do that well, I guess, at so high angle attack is maybe the delta wing, perhaps. Anyway, in figure 5, we see that pretty much for all cases, having a rider, so the blue line, results in worse bike performance, both the lift to drag ratio and in the drag coefficient. They're both higher, like by maybe 30-40%, and for the drag coefficient and for the drag ratio, a lot worse when you have just the rider and compared to no rider. Now, I don't know how much we can trust these numbers, but just for general interest, the differences stay pretty consistent across the entire wing's angle attack range. One thing that is very clear is that as the wing is pitched to more extreme angles of attack, the drag coefficient of the entire bike is severely increased. That shows that just how much of an effect these relatively small wings are having on the entire large motorbike. So we can conclude that the rider generally has a detrimental effect on the motorbike's performance, and that pitching the wings to greater angles of attack increases the drag. Now in figure 6, we see the effects of the different velocities on the single wing lift to drag ratio across the 0 to minus 51 degree angle attack range. It is clear that the velocity doesn't make much of a difference at all, really, which tells us that the wings are probably in the relative independent range from 20 meters per second already. And also, if you were to factor in the compressible effects, maybe that would change, but here we don't have that data. So I don't know the exact dimensions of the wing, but from this, the ones we do have, we can ballpark the radius number maybe around 200,000 perhaps. So maybe their placement on the motorbike makes them quite immune to the velocity as well. So from this figure, we can generally conclude that the best lift to drag ratio, so in this case the lowest because we want downforce, occurs at angles of attack between minus 35 to minus 40 degrees. In the next figure, figure 7, we now see in the left figure, the lift to drag ratio of case 3 AWK, which, just as a reminder, is the case where there are now 2 wings on each side. This figure shows the fixed wing above and the wing that can rotate in orange below. Let me zoom in a little bit here. Here we go. So the wing above, the fixed wing, was installed at the best angle found for the single wing in figure 6. So we saw that just before, that was minus 37 degrees, which is quite aggressive. So for case 3, the 2 wings may not be at the same angle of attack throughout the entire range. In fact, there's only one angle of attack where they are all at the same angle of attack, minus 37 degrees. The rest of the time, the lower wings are at different angles of attack. Now, I can understand why they decided to install the higher wing at the best angle found in figure 6, because that is the data they have, and they have already simulated a lot of CFD simulations. I mean, looking at all these angles of attack for these different cases, there are hundreds of simulations. So this is a huge effort and very thorough. So the researchers should be commended. But in terms of the best wing configuration, really both wings should be investigated at all different angles for both of them, and not just fixing one wing and investigating just the other lower wing rotating. Now, obviously, that would take more simulations, because for each angle of attack of just one wing, there are 51 other angles of attack for the other wing. So just for one velocity, you could have 2,601 simulations. That's quite a lot, too many. So I can definitely understand this limitation here. Anyway, let's move on with their results. So they found that for all angles of attack, having 2 wings on each side produced much better lift to drag ratios than having just 1 wing on each side. So compared to figure 6, we see here the minimum for figure 7 is minus 0.35 compared to minus 0.25 for the single wing. And while that is impressive, it shows that having 2 wings definitely reduces the maximum lift to drag ratio, the minimum, I guess. It is even more impressive when you look at the lift to drag ratio across the board. So for the single wing in figure 6, when you approach 0 degree angle attack, the lift to drag ratio gets bad very quickly. But for case 3, which is with the 2 wings here, and one installed at presumably a good angle attack already, even at close to 0 degree angle attack, the lift to drag ratio stays quite low at minus 0.23. So it's fairly flat, this line here. What that means is across the entire range, you're going to get pretty good performance still. So this additional wing, while it doesn't exactly double the best lift to drag ratio found for the single wing, it definitely makes the worst angle attack way better, no question. Now moving to case 4, which as a reminder is where you have both wings parallel to each other, and at any time the two wings can rotate at the same angle of attack together. So these wings are always at the same angle of attack. Now we see some really cool results. Let me zoom out a little bit so we can compare them a bit better. Here we go. So the best lift to drag ratio doesn't change between cases 3 to case 4. It still occurs at minus 38 to minus 39 degrees or so. There might be some small differences, but I think it might also have something to do with the uncertainty in the CFD. However, one thing that is really clear is that as the angle of attack approaches 0 degrees, case 4 performs really poorly and terribly. At minus 7 degrees, the lift to drag ratio has already become positive and the wings now produce lift instead of downforce. That's not what you want. So from this, we can conclude that having both wings rotate together isn't as good as having one wing, the top wing, fixed and the bottom wing able to rotate freely. Having one wing really fixed at a good angle of attack is crucial for good performance across the angle of attack range. So let's look at the difference in the wakes of case 3 to case 4 at different angles of attack to see why we are getting such differences in optimal angle of attacks and non-optimal angles of attack. So in figure 8, we see cases 3 and 4 at minus 41 degrees, which is really the best angle we've seen. So for case 3, the top wing is at minus 37 degrees, while the bottom one is at minus 41, and then on the right, we have both wings at minus 41 degrees. Now, we see some small differences that turn into potentially large differences, and I think this might be a little misleading in how exaggerated the effects are really with these figures. So that is because these effects are very rider dependent, and every motorbike is different, and even exactly how far the wings are on the front fairing, that is also different between motorbikes and the front fairing as well. So let me explain what I mean. On the left, we have two flows, one directed by the upper wing and one from the lower wing. Now, the way these flows are coming off, they hit the rider's arm, and that results in a much bigger wake downstream from the rider. On the other hand, for case 4, on the right here, the wakes from the wings kind of merge and then hit the rider's arm together, and then that somehow makes the wake from the rider's arm smaller. But all this depends on the rider's size and position, as well as the wing's placement, even wing profiles. So all these figures show that, generally speaking, the effects of the wings have on the flow, and the rider can be very different. I don't think the conclusions here are hard and fast. Instead, I think the only conclusion that can really be drawn is that these wings can have very different effects, and that needs to be considered on a case-by-case basis, as it stands at least, with this general information. Now let's look at case 5, which is, if you remember, is case 4, but the wings are joined at the wing tips, and that is for safety reasons. And in addition to that, let's also remember that they did LES simulations on this configuration as well as RANs to compare them, whereas for the cases 1 to 4, they only looked at RANs. So in figure 10, we see the differences in the wake results when they used RANs compared to LES. So the general wakes are quite similar, but as expected, the LES picks up much more turbulent structures, as expected. So one major difference that stands out to me is that over the bottom wing here, there seems to be more flow separation for the LES than for the RANs. So let me zoom in a little bit and look at this a bit closer. So this bottom wing here, you can kind of tell, seems to have a little bit more flow separation than with the RANs. And I guess you could say that the top wing, that also occurs, I guess you could say, but maybe for the top wing, the stall pattern is also different. So that is a major red flag for me, because these airfoils are what are creating the downforce. And if you're getting different stall patterns between the RANs and LES, that is not good. In addition to that, we don't see the lift or drag or lift to drag ratio forces and coefficients for the LES simulation. So I think, as we concluded earlier, the exact forces from the CFD should be taken with a grain of salt, and only the general trends should be really looked at and trusted, I guess. In figure 11, we see the difference in the vortices created without the wings on the top and with this AW5 case 5 package on the bottom. And there is a clear vortex string coming off the wings, which you don't get with the wingless motorbike. So here you can definitely see this passage here compared to here where there really isn't anything. Now in figure 12, if we scroll down here, it seems like this, and zoom out a bit actually, it seems like this vortex string comes from the flow from over the outside, spirals together with flow that goes inside between the two wings, and that goes together into this like vortex string, which is actually two vortices, these two vortex lines together and merging into one, I guess. And that's an interesting phenomenon, and it's probably powered by the pressure differences seen over the AWK. And with that, we come to the end of this podcast. Was really interesting because for me, I think the most interesting thing is that these wings performed so well at very steep angles of attack. I think that has something to do with how the motorbike is moving the air into the wing. And so while the geometric angle of attack might be minus 40 degrees or so, the effective angle of attack, in other words, the angle that the wings actually see, might be minus 10 or minus 20 degrees. And I thought it was interesting how having just one wing permanently installed at a good angle, as done in case 3, was hugely beneficial for off-design angle of attack. So finally, if you want to learn how to do overflow, which is a good CF, which is actually how the CFD was done, and it's probably because this CFD is so good, this package, and it's free, check out a link below. And if you are doing experiments, which unfortunately the CFD didn't validate against, did you know that you probably have a 2 to 4% error in your experiments and you don't even know it? We go through the math as to why in Atmosphere Hawk and how to correct that. So that's in the link below. And if you like this podcast, hit the like button. And if you want to see more like this, click the subscribe and or follow button, whichever platform you're on. And we'll see you next one. Peace, amigos.